Welcome. In this video, we're going to explain to you what rational and irrational numbers are. First, we need to know what the definition of a rational number is. That's our first objective today. Understand that a rational number is any number that can be expressed as the ratio of two integers. That's a fancy way of saying any number that we could write as a fraction in the form a over b, but a and b both need to be integers. We know from Monday that an integer is a whole number that could be positive, negative, or zero, and here's an example of a bunch of them. Our job today, once we understand this definition, is going to be classifying numbers as rational. Do they meet this definition? Can they be rewritten as a fraction? Or are they irrational? Is there no way to write this kind of number as a fraction? Let's take a look at some examples. It helps to start classifying our numbers right away. So we're going to look at fractions to begin with. Fractions can be complicated. They can be ugly decimals. 7 over 11, if I put that into a calculator, 7 over 11 would equal a messy decimal, 6363, that keeps repeating. That bar over the line there means that the 63 keeps repeating. But we don't even need to do any division. We don't need to worry about that if we're asked are fractions a rational or irrational number, because they're the very definition of rational. Can I write it as a fraction? Of course we can. All of these are already rewritten as fractions, so fractions are always going to be rational. Integers are whole numbers that can be positive, negative, or zero. Integers can always be rewritten as a fraction. All we need to do is put them over 1. 3 could be rewritten as 3 over 1. Negative 7 could be rewritten as negative 7 over 1. Or 7 over negative 1. 250 could be rewritten as 250 over 1. So we know every single integer is also always going to be rational, because they can easily be turned into a fraction by putting them over 1. Terminating decimals, this new term terminating just means that decimal numbers that come to a stop at some point could also be written as fractions. This has to do with our negative powers of 10. 0.5, we could move that decimal right once. We really know this is just 5/10, or 5 divided by 1 copy of 10. You would have called this number 5/10 in elementary school. We can see it just really means a fraction when we have a decimal number that stops. This number would be called 3 thousandths, which really means 3 divided by 1,000. So even the smaller, uglier decimal can still easily be turned into a fraction if we understand powers of 10. 3 copies to the right means we need to divide by 3 copies of 10, or 1,000. 15.025 we could rewrite as a fraction. It would just be 15 and 25 over 1,000, or 25 thousandths. We could simplify this fraction further, but we don't need to. We know terminating decimals, if they come to a stop, are also always going to be rational. A non-terminating decimal could be repeating. Non-terminating means it never stops, but it could be a repeating pattern. This looks like a familiar decimal to hopefully most of you, 0.66, where the 6 keeps repeating. As we saw up here, all of these repeating decimals actually came from fractions. The fraction 2 over 3, if I put it into my calculator, 2 over 3 makes 0.6 repeating. That's where this decimal number that repeats was created by, the fraction 2 over 3. 0.2 with the 2 that repeats forever, turns out it just comes from the fraction 2 divided by 9. That would create an infinite number of 2's after the decimal point. So this is also a fraction, 2 over 9. The important thing, every single repeating decimal was created by some kind of fraction. Here we see that the 1, 2, the 12 continues to repeat over and over again. It turns out that comes from the fraction 12 over 99. 1, 2, 1, 2 repeating. The important thing, every single repeating decimal, no matter how complicated it is, came from some type of fraction originally. So what do we know? Repeating decimals need to be rational. So what numbers might be irrational or not rational? We see fractions, whole numbers, decimals that stop, decimals that never stop but have a pattern. All of those are going to be rational numbers. A non-terminating, non-repeating decimal means that the decimal never stops, but it also does not have a pattern. The most common example of that is pi, which you worked with in 7th grade. You might have said pi is approximately equal to 3.14 in 7th grade. That decimal actually keeps going, and it doesn't have any pattern. It goes on for infinite number of places without a pattern. Pause the video and think, could I turn any of these non-repeating, non-terminating decimals into a fraction? Welcome back. Hopefully you realize that none of these non-repeating, non-terminating decimals could be created to fractions because we don't know how the numbers end. And if we don't know how the numbers end, there's no way to write them as a fraction. So this is our classic example of irrational numbers. Pause the video and think, are any of these square roots, are all of these square roots going to be rational or irrational? Welcome back. It turns out for square roots, it depends whether or not it's going to be rational or irrational. Perfect squares are always going to be rational. Those are those nice square roots that come out even. And the non-perfect square roots the ones that do not have a nice answer are always going to be irrational numbers. So let's take a look. Square root of 9 turns out is a perfect square. That's equal to exactly 3. Because of that, the square root of 9 is going to be a rational number. But the next perfect square is until the square root of 16, which makes 4. So that means the square root of 10 and the square root of 11, if we put those into a calculator, the square root of 10, the decimal doesn't stop here. The calculator for Google has to stop and round off at some point. There's no pattern, it keeps going. Same thing for square root of 11. We see the decimal doesn't actually stop here. Google needed to round off for its calculator. All of these square roots are imperfect squares, and they're going to end up being irrational numbers because they do not have an integer answer. Instead, they create a non-terminating, non-repeating decimal for the non-perfect squares.